Alright guys, today's lecture is on chemical reactions, and this is really a precursor, sort of very brief lecture in preparation for what we're going to discuss in the next section on enzymes. So all of life depends on chemical reactions, so that's correct. We have to go back and start talking about the chemistry and all the principles of how atoms move and are bonded together in order to understand the biology of things. For example, in this diagram here, we see a small amphibian, I'm going to guess some sort of a frog, that is being eaten by a Venus flytrap. And the process of digesting in that Venus flytrap using chemicals to break down the soft body tissue of that frog is definitely the result of a chemical reaction. So here is a list of your objectives. Remember, when you get to the end of this lecture, you want to come back and you want to read through these and make sure that you could answer them. If not, then go back through the lecture again, take some extra notes, and remember, you can always email your teacher. Okay. Alright, so in a chemical reaction, what we have is we have breaking and reforming of bonds. That's what causes a chemical reaction. So you have starting substances, which are called your reactants, and those are seen over here. Okay. So in this example, 6O2 plus C6H12O6. That's oxygen, and this is glucose, or a sugar. These are our reactants, or our starting materials. And then that's going to produce or yield, we don't say equals, we say it yields, the products, okay, which are those end results. And in this case, it is carbon dioxide and water. Now, if you notice, we haven't made any new atoms or subtracted any atoms. You could count, and all of the atoms here are accounted for. Okay? So in a chemical reaction, what we're going to do is we're going to break bonds that hold these molecules together, and we're going to rearrange them to produce new molecules. Okay? And those are going to be our products. Okay. All right. So we need to look at the energy that's involved to cause these chemical reactions, and that is considered bond energy. So the amount of energy needed to break a bond, that's where we're going to have to add in energy. Think about, when you're trying to snap a stick, right? You're applying pressure to that stick. You're putting energy into the snapping of that stick. So even though a lot of people think by breaking bonds that would release energy, that's not the case. You have to put energy in order to break bonds to allow them to rearrange. After they have been broken, there's a lot of energy there because those atoms are all searching for new bonding partners, and they finally find sort of a calm or a release of energy when they're able to form new bonds. Okay, so if we look here at this equation, we have carbon dioxide and water, and then on the product side we have carbonic acid. Alright, so in this case what has happened is these two things have combined together. And if you notice, we now have a new symbol in the middle here. We have an arrow going in the direction of the products and an arrow going in the direction of the reactants. And what that means is that the formation of products is equal to the formation of reactants. So chemical reactions can go backwards and forwards. It has to do with the amount of energy that is driving the reaction. So remember, energy is added or needed in order to break bonds, and then energy is released once those bonds form again. Okay, so how do we know how much energy is needed? Well, wherever we're starting, we need a certain amount of energy that's going to allow that chemical reaction to happen. So regardless of what kind of reaction you're looking at, unless it's spontaneous, we're going to need some sort of activation energy. So we need to absorb a certain amount of energy to start a chemical reaction. You can think of it this way, okay? If you look at this diagram over here, this young man is pushing a ball up a hill, okay? The idea is to get the ball to roll to the other side of the hill, but look how much energy he has to put into getting it up the hill. When does he stop putting the energy in? Once it reaches that top, because then the gravity takes over and it's going to lose energy, or you don't need to add any more energy in. So the activation energy is the amount of energy needed to start a chemical reaction. So we look at our reactant energy on this graph here, see how low it is, okay? It needs to go all the way up to here. And we're not using any sort of numbers, we're just keeping it very arbitrary, but what you can see is that there's an increase of energy that we need to absorb here, okay? Energy that needs to be put into the system in order to get the reaction to progress, which is your x-axis, going from reactants to products. So we can divide up chemical reactions based on whether they are absorbing more energy or releasing more energy. All right? So exothermic, exo meaning exiting or giving off. Thermic is referring to the production of heat energy. Okay, most chemical reactions are going to involve the production of heat energy. So exothermic reactions give off more energy than they need to take in. So let's take a look at this diagram on the bottom here. Wink, wink, nudge, nudge. You should be familiar with this diagram and then the one on the following page. So here's the energy of my reactants. This is where we're starting, okay? And I need to put this much energy into the system in order to get the chemical reaction to go, in order to go from reactants to products, right? To get that flow. Once we get to here, then my reaction can occur, and as that happens, look what's happening to my energy. It's decreasing, decreasing. Whoa, look at this. It decreases all the way down until it dips below where I started. So what has happened here is I have released more energy than I put into the system. Or in other words, my reactant energy was greater than my product energy. And what that means is overall, we've released more energy than we have absorbed. Typically, you're going to find catabolic reactions such as combustion being exothermic, and catabolic is describing the breakdown of molecules. So, for example, when you look at cell respiration, we take a really complex sugar molecule and we break it apart into pieces. So, in order to break it down, we have to input energy, right, to break those bonds. But then when those bonds reform into new molecules, those energies are so much less that it actually gives off more energy than it had absorbed. So I always remember catabolic because I think of a catastrophe. What does catastrophe do? It destroys things. It breaks things down, right? Buildings fall during huge catastrophes like earthquakes. Earthquakes are an example of a huge catabolic event. All right? The other kind would be endothermic reactions. All right? So in this case, endo meaning into, okay, endothermic, they're going to absorb more energy than they release. So now our reactants have a lower bond energy compared to the products. And in this case, our energy is absorbed. So let's take a look at this chart down here. Wink, wink, nudge, nudge. Make sure you star that. Here's our reactant energy. This is the amount of energy going up, right? This is our activation energy here. At this point, the reaction can occur now, so our products can become reactants. But by the end, when we get to our products, if you notice, we haven't released as much energy. Okay, we put in a lot more energy to get this to happen compared to what we have released. All right, we call this also an anabolic reaction because a lot of times what happens here is we have reactants where they're individual smaller molecules, and we're going to build up to a larger molecule. So instead of breaking things down and releasing that energy, we're absorbing that energy or trapping it in higher level bonds in that bigger molecule. All right, this is the case in photosynthesis. Plants take in small molecules like carbon dioxide and water, and then through a series of reactions, series of chemical reactions, they build that up to make a very complex sugar molecule. Well, all of that energy is stored in that molecule. It hasn't been released. It's being trapped in that molecule. So that's why at the end, the energy that's been released is not as much as where we were to begin with. So our total energy is here. Our energy line is above where we were with the reactant energy. So in this case, there was more energy that was added to the system compared to what we released from it. Okay? So make sure you understand the basics of this. Go back, take a look at the objectives, and then we're going to apply these concepts when we learn about the role of enzymes and how they can affect the rate of these chemical reactions that occur.